As we've said at the beginning of learning op-amp, the op-amp is one of the important parts of early analog computers. It still plays an important role in analog electronic circuits today. Therefore, next we will learn several practical circuits consist of the ideal op-amp and help you to grasp the analysis method of the ideal op-amp circuit with negative feedback. Besides special explanation, we consider that the ideal op-amp with negative feedback is operating in the linear region in this lecture. It has two properties, the virtual short circuit and the virtual open circuit. The virtual short circuit means U plus equals U minus, and the virtual open circuit means I plus equals I minus equals 0. As other analyzed circuits before, our analysis is still based on the element constraints and the topological constraints. The element constraint is the element's port property, and the topological constraint is KCL and KVL. Let's analyze some circuits with these properties. The first circuit is a voltage follower. The circuit is very simple. Based on the virtual short circuit property, obviously U minus equals U plus equals UI, and this line makes UO equals U minus. Then the relationship between the input and the output is UO equals UI. You may be confused about the function of this circuit since there's no difference between the input and the output value. So what's a characteristic of this circuit? Firstly, it has infinite input resistance. Seen from the input terminals, due to the virtual open circuit property between the non-inverting input and the inverting input, its input resistance is infinite. Secondly, it has zero output resistance. This cannot be seen directly from the figure. You can derive the output resistance after class. This is the assigned problem. We will take example to express a voltage follower's function. Now we have a voltage source U1, but we want to get a voltage signal less than U1. We can use a simple voltage divider circuit. That is, U2 equals R2 over R1 plus R2 times U1. However, once a circuit is loaded with RL, U2 and U1 don't satisfy the relationship anymore. In other words, the output U2 is changed with the load. Of course, it isn't what we want. Now connect a voltage follower to U2. Let's analyze again. It's a circuit with a negative feedback, and the virtual short and the virtual open is applicable. You can see, based on the virtual open property, the current I through this line is always 0. So U plus always equals R2 over R1 plus R2 times U1. Based on the virtual short property, U2 equals U minus equals U plus. So U2 equals U minus equals U plus and always equals R2 over R1 plus R2 times U1. The change of the load has no effects on the output. That's a voltage follower's function. It's often used to separate two parts of the circuits. The second circuit is an inverting amplifier. Our analysis is still based on the virtual short and the virtual open properties of the ideal op-amp. Based on the virtual short, U minus equals U plus. Based on the virtual open, I minus equals I plus equals 0. I minus is 0 means I1 equals I2. Now that I1 equals I2 and U minus equals U plus equals 0, since U plus is connected to the ground, then we get I1 equals UI over R1, and I2 equals minus UO over RF. Then the relationship between UO and UI is UO equals minus RF over R1 times UI. The proportion coefficient between the input and output is negative. That's why it's called the inverting amplifier. Now we use the experiment to verify the function. We can also discuss other important notes in the experiment. Now let's do the experiment of the inverting amplifier using the op-amp. The coefficient is minus 4.2. The input is a sine wave. We use the oscilloscope to watch the input and output waveform. Now you see the input and output waveforms. Channel 1 is for the input, channel 2 is for the output. With current voltage, the output is a linear amplification of the input, and they are also with opposite phase. Now we increase the amplitude of the input voltage. As we can see, when the input reaches a certain value, the output enters a saturation. Now the circuit is not the inverting amplification anymore, because the maximum output of the op-amp cannot be higher than the power supply. Okay, let's see the third circuit, which is a non-inverting amplifier. Our analysis is still based on the virtual short and the virtual open properties of the ideal op-amp. The virtual open means I plus equals I minus equals 0. The virtual short means U plus equals U minus equals UI. U plus equals UI because the current through this line is 0. UO equals R1 plus R2 over R2 times U minus. Substitute the relationship between U minus and UI, we get UO equals R1 plus R2 over R2 times UI. The proportion coefficient is positive, so it's called the non-inverting amplifier. Different from the proportion coefficient in the characteristic of the inverting amplifier, UO equals minus RF over R1 times UI, whose absolute value can be larger or less than 1. Here, the proportion coefficient of the non-inverting amplifier is always larger than 1. So please think about how to design a non-inverting amplifier with a proportion coefficient less than 1.